Hi guys, it's time to learn some more electronics on Learn Electronics Repair. So, if you've been watching this series so far, we've looked at some very basic circuits, but now we're going to look at something that is very important. So, this is probably one of the simplest circuits you will find in the electronics. You find this used everywhere, and it's very useful. So, I'm going to show you what you can do when you connect two or more resistors in series and why this is important in the electronics. So when we say connect in series, it's like a daisy chain, one end to the other. If they have daisy chains these days, of course. They did when I was a kid, but anyway, that's the way I describe it. So if we take two resistors and we put them in series like so, and we connect a voltage across the resistor. So let's say, for example, we put 10 volts because it's a nice round number. Okay, so we put 10 volts across our resistors. What voltage do we get here in the middle? Yeah, what voltage do we have in the middle? Well, let's try. Let's do a few experiments and see what actually happens. And then we'll come back to the paper and we'll explain this, what's going on, okay? So first of all, we need some resistors. And here we have some. So these have the color code, orange, orange, brown. Hopefully you watched the video on all you need to know about resistor color codes. To fix stuff, you will know the value of this. So orange is 3, orange is 3 again. So we have 3, 3. And then the brown is actually 1, and it means 1, 0. So it doesn't mean the value is 331. It means the value is 3, 3 followed by 1, 0, which is 330. Let's measure these resistors and see if that is actually correct. Now you will see, in fact you may have noticed, the last band here is gold, so that means 5%. So that means the value of this resistor is 330 ohms plus or minus 5%. What's 5% of 330? Well, 10% is 33, so half of that, yeah. So about 16.5 ohms either way. So this 330 ohm resistor could be quite a few ohms out and still be within its tolerance. So let's see what we have. So this one, well, it reads 327. Okay, so it's reasonably close. This one, 329. So you see they're not exact, but we're going to put these two resistors in series and we're going to measure the voltage from here. So this is 0 volts. This is your 0, if you like. This is often called ground. So if you ever wonder what ground means in a circuit, it's actually the point of reference you use to take your measurements from, and we consider ground to be 0 volts. Is it really 0 volts? Well, not necessarily, but because we use this as our reference, we consider it to be 0. More about this in the next video, I think. But for now, let's accept that ground is 0 volts. And ground has several symbols. It has a symbol like I've drawn a line. It has a symbol like this, which is earth, if you like, or ground. It can also be represented like this. Sometimes this is called chassis. Okay, and it can also be represented like this with a solid black bar. Often this is called hot ground, and we'll talk about that in the video which we'll make just about ground. But for now, there are different symbols. But from our point of view, this means 0 volts. Okay, so this is where we attach our black meter lead and we put the meter into volts range. Again, couple of videos down we will talk about multimeters if you're not familiar with them, but this is a basic operation of a multimeter. We then take our red lead, and if we put it here, well, if we put in 10 volts in, we will see 10 volts on the meter. If we put it here, what will we see? Well, let's have a look. So here's our circuit. You can see we have the two 330 ohm resistors in series. let's measure the voltage. So I've set the power supply to 10 volts. If we measure here, we have 10 volts, close enough. Okay, so what do we have on the junction between the resistors? That's this yellow wire. Well, we have 5 volts. So we have half the voltage across this bottom resistor, because I say the bottom because this green lead, this is the ground for my meter, so I'm measuring with reference to here. Okay, so we can see we have half the voltage across this resistor, and if I want to, I can measure from the junction of the resistors to the end of the other one. So I'm measuring across this resistor, and we will have 5 volts. This is slightly different because we know the value of the resistors was slightly different. So using two 330 ohm resistors with 10 volts in, we get 5 volts on the junction, half. Let's try some other resistors. So we'll disconnect these. These are much higher value resistors. So these are 470 kilo ohms. So reading from this end, yellow is 4, violet is 7. And then the other yellow means 4 zeros. So we get 4 7 0 0 0 0, which if we write it out on paper is 470,000 ohms. So let's put these into our circuit. Okay, there are our resistors. Yeah, 470, very close. So let's connect our power supply back on. I'll connect my negative or black meter lead to the ground again. This 0 volts, the negative of the power supply. We'll switch on. What do we have? What do you think we'll get? Well, we still have 10 volts coming in. What's on the junction? 4.93. So again, it's half basically within the tolerance of the resistors. So using two 390 ohm resistors or two 470,000 ohm resistors, we still get the same voltage. Half. Okay. Let's try something else. Here we have another resistor. So we have yellow, violet, black, red. So this has 4 bands in the value color code, where this has 3. The last band, brown, is the tolerance. This gold, this is a 5% tolerance. This brown, this is a 1%. So this resistor is made to a closer tolerance. It will read closer to its actual stated value than this one. So again, we have yellow is 4, violet is 7, black is 0. So in this code we have 3 digits, 4 7 0, and then red means 2 more zeros. So 4 7 0 0 0. That's 47,000. So whereas these were 470,000, this is 47,000. This is a tenth of the resistance of that one. Let's put that in the circuit. I'll leave the other 470k in, and we'll put our 47k in. Now, what voltage do we have across the resistors? Again, I'll measure with reference to ground. So at the junction, we now have 0.9 volts. Okay, and here we have 10 volts. So if this one has 0.9 across it and both have 10 across it, I think you can work out that the other one, and we'll measure it, has 9.1. Because it must add up to the total value, 9.1. So you have 9.1 here, and we have 0.9 here. So the reading on that one is 10 times the reading on this one, voltage. And that's no coincidence, because this one is also the 10 times resistance of this one. Let's put that on our paper. So what have we learned? Well, we've learned that the voltage on the junction is a proportion of the voltage coming in. And we've seen that if we put two resistors of the same value, so we use 390 ohm, 390 ohm, the voltage here was half of the total. So this was half of that, 5 volts. And then we tried this again with 470,000 ohm resistors, 2 of them. Again, they're equal value and the voltage was still 5 volts. So the voltage doesn't depend on the value of the resistors. What does it depend on? Well, we prove this on the next experiment. So on the next experiment, we had 470,000 ohms here, and we had 47,000 ohms here. 470k, 47k, that's the way they would be written. What did we find? Well, we found if we measured from here, so measuring across this resistor, we had 0.9 volts. The total is still 10, that hasn't changed. And if we measure across this one, so this is our meter connected, we had 9.1. So basically the value here was 1/10 of the value coming in, and this was the other 9/10. Okay, this was 10 times less across here than there, and the value of the resistor was 10 times less. So straight away we can see we have a relationship here. Depending on the ratio of the two values, we will get a given voltage on here, and the voltage will depend on the ratio of the two values, not the actual value of the resistors. Now, you know, I don't like doing mathematics on this channel, but the mathematics to work this out is so simple, I'm going to show you. How do you work out what the voltage is going to be? Let's just draw some resistors. Let's give them some values. 27k, 27,000, okay? We'll have 10 volts on here. Let's think of some other value. I don't know, 6.8k, 6,800, okay? And this is ground. What voltage do we have there? Well, first of all, we need to draw a symbol on here so it looks like a resistor. And secondly, we need to use a very simple formula. So to work this out, what we do is we add together the resistors to get the total. So 27,000 plus 6,800. Okay? What's that? Let's see. Well, for those of us who can do mental arithmetic, this is very easy because 27 and 6 is 33, so the total is 33,800. For those of us who can't do mental arithmetic and rely on a calculator, you will find that the value is 27,000 plus 6,800 is 33,800. So it's still the same value, it just took you longer to do that than it would have if you just did it in your head. Yeah, there you go. So we know the total value is 33,800. How do we work out the voltage here? Okay, well, we take 10 volts, so we have voltage, okay, we divide it by the total resistance, that's the resistors added together, and then we multiply that by whichever resistor we want to know the voltage across. So if we want to know the voltage across this one, we'll call them R1 and R2, we multiply it by R2. If we wanted to know the voltage across that one, we multiply it by R1. Let's work this one out. So 10 divided by 33,800 times R2, 6,800. We then realised that my little ploy about mental arithmetic doesn't always work, it's not always quicker, although I could do this one quite easily, and we work it out. So we have 10 volts divided by 33,800, that's the total of the resistance all added together, equals 0.000295. Yeah, 58. and we multiply that by the resistor we want to know the voltage across. So times 68,000. And it comes to 2 volts, 2.01. So we know from here to here is 2 volts. Yeah, on there. We can see straight away now that if that's 2 volts, this must be 8 volts because there's only 10 to start with. It can't be more than 8 and it can't be less because otherwise where is the voltage? But we can work it out just to prove that our common sense really is common sense. Okay. 10 volts divided by 33,800. Yeah. And then we multiply that by 27,000. And it equals, we can call that 8 volts, can't we? 7.988. So the other 8 volts is across here. Now we know the mathematics is good, but the only way to prove this is to take the 2 resistors and we'll make the circuit and we'll measure it, yeah? And once we've done that, we know with confidence that this was correct. So let's do it. Well, here are our 2 resistors. So this one is 27k. That's red, violet, orange. So red is 2, violet is 7. So it's 27 followed by orange 3 zeros. We can measure it just to prove it, but that is a 27k. We will measure it. And the other one, well, this is a 6.8. So blue is 6, grey is 8, and red is 2 zeros. So 6800, 6,800, 6.8k. Let's check it. Resistance range. So this is our 27k. It doesn't matter, by the way, which way you measure the resistor. So if I measure the resistor this way, I read 27k, and if I measure the resistor this way, we get 27k, and this one was 6.8. Yeah, 6.72. So you can see also it doesn't matter which way you measure it, 672. So those are our resistors. We calculated this and came up with a value on the junction of 2 volts on the yellow wire. So let's see what we actually have. So this is our ground, or 0 volts. This is our supply voltage, 10 volts. I'll now connect to the black meter lead to the negative of the power supply, ground. And what do we have across this resistor? What's on the yellow wire? Well, we have 2 volts. Okay. So that's how you work out the voltage across any resistor when they're wired in series in this potential divider. This is called a potential divider, if I didn't mention it before. Potential divider. Potential because that's the voltage, the potential. The pressure, if you like, the electric pressure. And divider because it divides it. You can, by the way, just mention this, you have circuits like this. Ground, that's not the ground symbol. Values could be the same or different, voltage could be whatever. And this is a potential divider with 2 taps. Because they're all the same value without doing the maths, and you could do the maths, so what you would have to do is add all these 3 together, giving you 3,000, divide 10 by 3,000, and then multiply it by 1,000, and you will find if you do that, you've actually got 3.33 volts on each one, 6.66. Okay, rounding error says 9.99, but it's close enough, yeah. Volts. So you'll sometimes find circuits like that. Now, here's a question. If it doesn't matter what the value of the resistors are, it only matters what the ratio of the values are, what values do we select? Does it matter? Why should we use a high value or a low value resistor in the divider? Because the voltage is the same, yeah, we've proven that. Well, the reason we need to select the values is because this 5 volts is doing something, yeah? We're not going to make this 5 volt for no reason. We're doing it for a reason. We're doing it because we want to use the 5 volts for something. And the something, no matter what it is, will be a load. It's something that draws some power from here. Whether it's infinitesimal, so small it's hardly detectable, or whether it's large, you will have a load. And a load basically is just another resistor. Okay? And that resistor, the load, is in parallel with this one. So this will effectively, you saw the video on resistors in series and parallel, you know that the resistor in parallel effectively reduces the total resistance. So when we put a load across here, we're reducing the total resistance here, and therefore we're affecting the voltage there. The more power the load draws, the lower the resistance of the load, the bigger the effect becomes. So effectively we need to reduce the value of both resistors to supply more current so the load will not drag this voltage down. It will always reduce it to some extent, but we can, by choosing the values that we use and knowing what current the load draws, we can make it so that we get the desired voltage on here. Okay? Second question. Seeing as we can vary the voltage on here, we've got a variable voltage supply, yeah? So what if we use a variable resistor? That's a resistor that you can vary the value. And the symbol is that, the most common one. Well, let's have a quick look now at a variable resistor and see what happens with the voltage. Okay, here is a potentiometer or a variable resistor. Yeah. What we have inside here is a copper track, like so, like a circular track with little connections on the ends, and we have a wiper. So we have a metal wiper that actually goes across the track. Best way to demonstrate this is to open one up and show you. You can generally do this without destroying the potentiometer or variable resistor. You can put it back together again. Potentiometer is a strange name because it's like a potentiometer, like it's a meter. It sounds like it measures stuff. Meters measure stuff. It doesn't measure anything. Okay. Call it a variable resistor if you prefer. So we'll just lift these little tabs up. Okay. And inside you will see we have a track, you can see it, connected between the two ends. Can you see the connections going in either end onto the track? And we have this wiper or slider that slides along the track, and the slider is connected to the middle pin. Okay, so that's the potentiometer. I'm sure you can now see the little connection going up the middle from here to here. So that's how it actually works. This one I've just dismantled has a value of 50k, 50 kiloohms, 50,000 ohms. If you're wondering what the B is for, it specifies the type of potentiometer. So briefly, you can get potentiometers that alter in a linear fashion. So if this is 50k on a type B or linear, halfway will be half, 25k. Okay, that will be 3/4. This will be 1/4. This will be 10%. This will be 90%. So the value alters in linear fashion. Okay, you can also have type A, which are logarithmic. So that basically means that at one end, at first, you get a small amount of resistance change. And as you turn it around, the amount of change per degree angle increases. So at this end, for example, you'd have a very high amount of change. Those type are called type A, and they're normally used in audio equipment. It's a factor of the way the human ear works and sound pressure levels work, that they use logarithmic scales basically. So to get something that sounds twice as loud to you requires 10 times as much audio power. That's the basic theory of it. You can remember quite well. So if you remember A for audio, then you'll know that those are the ones which are logarithmic, if you just remember that. The other ones, well, they're linear. That's B. That's the way I remember it. A for audio circuits. Might not always be the reason they use, but it's a good mnemonic. So let's look at ours. B 1K. So B means it's a linear adjustment. 1K is the value, 1000 ohms. So let's connect this to our circuit and let's measure the voltage on the center pin. So to do this, I'm going to connect 10 volts here. I'm going to connect 0 volts here. And I'm going to connect my meter between the 0 volts and the slider, okay? So I'm going to measure the voltage on this slider. I'm going to adjust it and see what happens to the voltage. So here is my circuit with my variable resistor or potentiometer. So I've connected the red meter lead to this white crocodile clip. It's on the center there. And the black one is connected to the black here. And this is the 10 volts coming in. So I've now adjusted the potentiometer all the way clockwise. And I can see 10 volts. And if I go all the way the other way, I can see practically 0 volts. And if I set it somewhere in between, I can get somewhere in between. Okay, and I can continually vary this. When I set it to 5 volts, I'm in the mid position. We could measure and we could see that we had equal resistance, but probably if I just put a knob on this, it'd be clearer. Okay, you can more easily see now where the position is. So by turning the knob, you can see that is about 50%. I'm on 5 volts. That's all the way. So there we have a variable output power supply. Yeah, and it goes between 0 and 10 volts. And if I put some more voltage into here, so I can go up to say 12 volts. I've now got a variable power supply. Look, 6 volts, whatever. And the first time I saw this, when I was nothing but a young whippersnapper, I thought, wow, I can make a light bulb dimmer out of that. Yeah, I mean, I wasn't messing around with mains voltage stuff, but I had light bulbs out of cars, old ones from I found on the scrapyard, because I had scrapyards around, and as kids we used to play on them, basically. So I went down to the scrapyard one day and found some 12 volt bulbs, and I brought them back, and I had this connected to my Scalextrics transformer, which was 12 volts, and it would light the light bulbs, and I connected it to my light dimmer, and I thought, let's see what happens. So I want to recreate that experiment for you now, and in doing so, I'm going to show you what I learned that day. So let's look at my circuit I built. One of the first things I ever did with electronics. I chipped my variable resistor, which no doubt I salvaged out of an old scrap radio I've also probably found somewhere on the wasteland or around the scrapyard. Okay, and I connected my resistor like so, and I put my light bulb here. Okay, and this is the negative end of my Scalextrics transformer, and this was the positive end, 12 volts. And I thought, well, if I adjust this to the middle, I'll have 6 volts on the light bulb, will be half brightness, yeah? So this is what we're going to do. And I'm going to measure, so I'm going to put my test meter. I didn't have a multimeter when I did this, so it took me a little while to understand what was happening, but of course these days we do have. I don't remember where I got my first multimeter, but I guess somebody bought me one for Christmas or something at one point. And they were analog then, not digital, of course. So here's our light bulb. This is a courtesy light thing, you know, the roof of your car that lights up when you open the doors. It's that sort of thing. It's 12 volts. And I'm going to connect that to the wiper of our variable resistor here. I'll turn this all the way down first. I'm going to start, I want it dark to start with. I'm going to do that, so we're going to put my light bulb on here. And then the other end of my light bulb, well, I'm going to connect this to the black lead, okay, the negative end. And we're ready to go. We've got 12 volts coming in. We've got our light bulb we found on the scrapyard. We've got the variable resistor out of the old valve radio that we found. And I'm ready. Okay, so I didn't have a voltmeter. So what I started to do was just turn up the voltage. So I'm turning the resistor along now. So I'm actually turning it to about halfway. But do I have 6 volts across the light bulb? Well, no, I don't. I only have 0.34. It was only like 0.17, or sorry, 0.017 to start with. And I've now got a little bit more, but I'm not getting much voltage here, yeah? And why am I not getting much voltage here? Well, I didn't probably realise at the time, but the reason I'm not getting much voltage here is because of what I've just described. My light bulb is a load, and it's in parallel with my variable resistor, or like on this potential divider. So the resistance here is actually much lower because this is in parallel with it. So I need to turn it up more. But okay, if I keep on turning it up, I should get to a point where I have some voltage on my light bulb, yeah? And it lights up dim, and I can adjust it. So we keep going, and we got a little bit more. And I keep going, and I keep going, and nothing really happening. And now I've got a bit, oh, because it's lit. But look what's happening. And that's what happened. That's what it did. That smell of burning, it's delicious smell of burning electronics here, yeah. That's what happened. Bit more, yeah. Mine actually set on fire. Maybe they make them a little bit better these days. Maybe I just don't have it in quite the right position yet. It's gone. It's gone. It's dead. No voltage, no light bulb. I had a dimmer for a few seconds, but then, well, that was the end of that, yeah. So what's happened? Well, this is very hot, but we want to see what's happened to it, so let's have a look. I can't even touch it yet. So I'll explain on the paper. We'll let that cool down a bit. What happened is this. We had 12 volts. This is my variable resistor. Okay, and this is my light bulb. And this is 0 volts. So at the point I adjusted this, so I had about 6 volts across here. Okay, I also then had 6 volts from here to here. Okay, and the light bulb's lighting up, it's drawing some current. This light bulb is a 22 watt light bulb, so it's half brightness. Without getting into the semantics of it, we could say it's drawing 11 watts of power. But it's a 22 watt light bulb. Where's the rest of the power? Well, the rest of the power is across here. So that's where your 22 watts of power are. 11 across the light bulb and 11 across your variable resistor. The light bulb, well, it can handle that and it lights up dim, what we expected. The resistor, well, it can't handle that because this variable resistor has probably got a maximum rating of 1/4 watt, and I'm sticking 11 watts on it, and that's why it's smoldered. Let's look what happened to it. Well, here's our variable resistor. It's cool enough to touch now. It took quite a long time to cool down, and we can see that the carbon track in this area there is burnt up. We've actually burnt the carbon. It generated so much heat. The carbon track got so hot it's actually melted part of the plastic, and I suspect what's happened in the end is that this lost contact. Yeah, the little slider effectively lost contact, or we just burnt away the carbon, but probably lost contact. So that's what's happened. When I did this as a youngster, I didn't really understand it. I thought it was very interesting, but I didn't really understand it. I suspect the next time I got another scrap variable resistor, I repeated this experiment to find the same thing happened again. And it was some time before I actually understood what was going on here. Later I was reading more books from the library and understanding Ohm's law. I think quite possibly at the time I was in high school, I asked the physics teacher, showed him what I was doing, and he actually explained some of that to me. So that's how I learned it. But you guys, hopefully you've already learned it, yeah? So I hope that was fun. Hope you've learned quite a lot. Anything that you want to know on this topic, please, only because this is a tutorial guide, step by step. Anything on this topic, comments below. And if it wasn't any clearer than mud, well, just ask and I'll see if I can make it clearer. If I have to demonstrate more on video, of course I will. Okay, so I hope you enjoyed that, and I look forward to seeing you all soon on the next lesson. Ciao for now, guys.